Okay, this is going to be a video on how to get started on these Chapter 11 problems. So let's just dive right in. You can reference my solutions as well for the full answer. This is just going to be to get you going a little bit. So on this one, we've got a cylinder that's sliding down the roof, and then it's going to fall, and it's going to hit the ground over here. This is a classic kind of two-system physics problem where we've got conservation of energy here, along with rotational motion, and then this is just a projectile problem that's down here. So the first part is really just figuring out how fast this thing is going as it exits the roof over here. So we're looking for what's the speed v right there. So this is a conservation of energy problem where we've got something that's up a particular height, and we're trying to figure out how fast it's going at the bottom. So we kind of need this height right here. So to set up conservation of energy, we're just going to say we're starting out with some gravitational potential energy, and that's going to turn into some translational kinetic energy plus some rotational kinetic energy, right? And now we're looking for sort of V right here. Omega and V are related to each other. Just remember omega and V are related to each other by omega is V over R. So I'm going to put in a capital R right there because I'm dealing with an object that's rolling down the hill. We have to figure out what's this height right here, this h, and to figure out the h, we just really have this L times the sine of this angle. So it's L sine theta. So this is mgh over here. Good. That's what the gravitational potential energy is. So I'm just going to leave it as h for now, and I'll plug in, you can plug in L sine theta later on. So then the part of the trick is also just remembering what the I is right there. So this is a solid cylinder. So looking over here, that's a disk. Disk is the same as a solid cylinder, so it's 1/2 m r squared. So if I stick this in there and I stick 1/2 m r squared in, this whole thing's going to change a little bit. So let's just write it out again. So I've got mgh equals 1/2 mv squared plus 1/2. The I here is 1/2 m r squared, and then I've got omega is v over r, so that's v over r squared. And it's nice to do it this way because now my r squareds cancel and my m's cancel. Good. And now it's just some algebra to figure out what v equals. And that's actually not so hard to do. So you figure that out, you'll figure out what v equals. Now that's the speed v as it's exiting the roof over here. So if we kind of draw a little diagram here, let's just do it down here. There's the cylinder, and it's leaving the roof with the speed v right there. And we're trying to figure out how far it's going to go when it hits the ground over this way. So what we need to do is we need to split up. Oh, sorry, that's a little bit too low. There you go. So here's the cylinder, and it's leaving the roof at a speed v, and it's going down like that. So what we need to do is break up this v into components. So we're going to have a v in the y direction and a v in the x direction. And we're really trying to figure out what's this x distance right there. So in the x direction and the y direction, we have sort of two different problems that are happening. In the x direction, we just have the distance is going to be the x direction speed times the time. Of course, we don't know the time, so in the y direction, we need to figure out the time. In the y direction, we've got a distance that we've gone, and we've got an initial speed, and we need to figure out the time. So we have to use this whole 1/2 at squared plus v0t plus y0 equation. To figure out these components, by the way, we kind of need to figure out what this angle is. And if I draw this kind of extended up this way and draw this dashed line here, here is the original angle that's given in the problem. So that's this angle down here, and this angle is going to be 90 minus that angle. So if the original angle back up in the problem was 30, then my angle that I'm dealing with right here is going to be 60. So maybe I'll call that theta 2 or something like that, so that my components are going to be based upon theta 2. So my Vy is going to be V sine theta 2, where theta 2 is this angle of 60, and then my Vx is going to be V cosine theta 2. Or I could have just switched it as sine of the original angle for this one and cosine. Anyways, you get the idea. The trick with this one, once again, is just remembering that if you choose this as y equals 0 at the ground, then in this equation, when you're plugging things in, I'm looking for at what time will the cylinder reach the ground at 0. So I'm looking at 0 equals 1/2 I'm going to do negative 9.8 t squared plus, this is going to be my Vy right here. Vy times t plus my height right here, h. Cool? So now solve this for t. It's a quadratic. It's kind of a pain. I think in my solutions I didn't solve it right. And so like here's my solutions, and I think I didn't solve it right. So I think this was not the right solution. But anyway, solve it for t and then plug it in over here and you can find x. So it's a long problem, but it's doable. Just take it one step at a time. Okay, this next one goes to this diagram over here. So let's just get this up here. We have a solid brass ball, and you got the mass of it, and it's rolling along, rolling smoothly. It's going to roll around here, and the ball has a radius r much, much less than r. So what that means is we don't have to, when we're dealing with the ball, we can just deal with it as like a point. We don't have to deal with like the center of mass of the ball being different than where it is on the track. That's why we need to know that the radius of the ball is much smaller than the radius r right there. So we're just going to assume when the ball is over here that it's just touching the track right there and not having to deal with like I said, the center of mass being lower than the track. We're not given the radius of the ball itself, so we're just going to leave that. Must mean it's going to cancel out. We have this height right here is 6r, and we're going to do some things. It says, what is the height h? What is h if the ball is on the verge of leaving the track when it reaches the top of the loop? So we're going to deal with the ball right here, and when something's on the verge of leaving the track, that means that there's no normal force. So at some point, if we're going to need to draw a free body diagram at that point right there, the free body diagram is just going to look like this. It's just mg down with no normal force at all. There could be, if you're going faster, there'd be a bigger normal force pointing down, but there's no normal force right here. So that means that if I write a net force equation, F net equals ma, I just get mg. But remember, this is going around in a circle, right? And when things are going around in a circle, then the force on them, the net force on them is mv squared over r. Actually, I'm going to put it as capital R, since that's this big radius right here. These m's will cancel out. And what I can do is I can actually figure out how fast it's going. I'm going to leave it as v squared. I think that'll be easier. Is just going to be r times g. Cool. So v squared is r times g, and that's going to come in handy later on. That's the speed of the ball at the top of the track right here based upon what this radius is. The other thing we can do is we don't know what r is and we don't know what v is, so we can't really solve anything over here. But what we can do is we can use conservation of energy to figure out how fast the ball is going here based upon how high it started. So it's a energy conservation thing. I've got some potential energy here, and then I've got potential plus kinetic energy over here. A couple ways we could actually do this. So I could say what I just said, that right here I've got some potential energy, and over here I've got some potential plus some kinetic. And I've got two types of kinetic. I've got rotational kinetic and I've got translational kinetic energy. The other way that I could do it is I could just kind of make this my ground level, and I could say the potential energy here is just based upon from there to there, and I could eliminate this UG on that side. So why don't we do it that way? I think I did it a different way in my solution. So once again, I'm going to say this is the zero height for this particular part of the problem. I'm going to base my mgh on the difference between there and there. So how high is that? Well, if this is 6r and this is 2r, then this height right here must be 4r, because I've got 2 left over. It doesn't really look like proportional, I guess. Oh, wait a minute. No, this is totally wrong. So, sorry, going back to the problem here. What is h if the ball is on the verge of leaving the track when it reaches the top of the loop? And then the next problem says if the ball is released at a height of h equals 6r. Okay, so that's the next problem. Okay, so never mind about what I just said. We have to base this. We don't know what this h is in terms of r. So we're just going to leave it as that. So we have potential energy here and potential plus kinetic over here. We're looking for something where we get a v equals out of it. So let's just write all this out. I've got an mgh, and that's originally. And now this potential energy here, I'm going to have mg, and then this is going to be 2r, because that's how high this is above the ground. I'm going to add in the rotational kinetic energy, 1/2 I omega squared plus the translational kinetic energy, 1/2 mv squared. Ostensibly, the mass is going to cancel. Even though we're given the mass right here, I think the mass is going to end up canceling out. So what are we doing with all this? There's a lot going on in here. We're going to take this I, and we're going to substitute this I in for the I for a ball. So the I for a ball over here is going to be 2/5 mr squared. So that's 2/5 m. I'm actually going to leave it as a little r squared. So because this r is not the same as this r inside of here. This r is how high up this is. This r is going to be the radius of the ball. So just to make sure that we're keeping those things straight. This is sort of kind of what we're looking for in relation to this over here. So or I guess we're looking for h over here. So that's fine. So that is going to plug in there. We're also going to take that omega is, I guess, should we do it this way? Yeah. So omega is v over r. And once again, I'm going to have a little r in here because that's now the radius of the ball. And then this v squared over here, look, we know that that's rg. So I might stop here for you and just have you go for it from here, because you're going to put this in for there, you're going to put this in for there. This r is going to cancel, so we'll get rid of that little r, which is nice. The m is going to be here, 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 and here, so that m is going to cancel. Put this into there, and then we're trying to figure out what h equals out of this whole thing. So yeah, good luck with that one. I think maybe we can get it. We have r, by the way. We have what capital R is, so you can always plug that in. So yeah, go from there. And yeah, it's a tricky problem, but I think you can get it. Okay, moving along. Here's number 31. We have a ball, and it's being shot upward with an initial speed. And it says, what is its angular momentum about this point, horizontally from the launch point, when the ball is at its maximum height and when it's halfway down to the ground? And then we'll talk about the torques. So when we're talking about the angular momentum of just an object, angular momentum over here is L. If it's something that's a solid object that's rotating around, you know, like you get a ball that's rotating, then that's going to be I omega. But if it's just one single object that's moving, like this bullet right here, then it's mvr times sine of theta. So what we need to do is we need to figure out the velocity. And then this r sine theta is going to be really interesting. So let's talk about that r sine theta real quick. So down here, if I wanted to figure out the angular momentum of the ball right here, I could have its speed v, and then the r would be here, and my v and my r are going to be at right angles to each other. So I don't really need to deal with this r sine theta. When the ball is like, say this is its maximum height right here. Oh, well, the maximum height, that's actually interesting and maybe a little bit silly, because at the maximum height, the ball is going to have zero velocity. So when it says find the angular momentum of the ball at its maximum height, the ball has zero velocity at the maximum height, so it shouldn't have any angular momentum, I think. At least that sort of makes sense to me. But when the ball is halfway down, so let's say it says when it's halfway back down to the ground. So when it's halfway back down to the ground, I'm going to get a v right here. Now my r is going to be right there, like that. So there's my r. So in this formula, mvr sine theta, I have to find the angle between r and v. Now the way that we really need to do this is I need to take r and v and I need to put them together, their tails together. So I would have r going this way and I would have v going this way. And this would be the angle between them that I'd plug in up over here. So sorry, you can't see that. So once again, this is the r and this is the v, and the angle between them would be this if I'm plugging into this formula. But the way that I've written it in my solutions is I also write it as m, v, r, and I put a little perpendicular sign inside of there. What that means is that at any particular point where this ball is going, like this, I can make a dashed line down to where the velocity of the ball and the distance between the ball and the rotation point are at right angles to each other. And I can just use this as my r perpendicular. So I'm going to write that as r perpendicular. That kind of takes care of the sine theta part in here. So you can kind of imagine, like, if the angle is here, it's not exactly this angle, but the sine theta is sort of the opposite. I have r, I have sine theta, but this is called the r perpendicular right here. So once again, it's just take my velocity, my ball, and wherever it meets the path at a right angle, then this is the r that I'm going to use right there. So this is where I have mv r perpendicular. Now the only tricky thing left is to figure out what is the velocity when it's halfway back down to the ground. So a couple ways we can do this. I think probably the easiest way is to figure out its maximum height and then figure out how high it is when it's halfway to the ground. And that's how I did it in my solutions as well. So this is just going back to some kind of kinematics formulas. So to find its maximum height, what we're going to do is use this equation. V squared is v0 squared plus 2a, I'll put it as delta y, since we're going in the y direction. This is going to be 0 at the max height. This is going to be 40 plus 2 times 9.8, and then delta y inside of there. I think we should use negative 9.8 here, since that was a positive number, and this is going to be a negative number. So then I can figure out what my height is right here, my delta y. That's its maximum height. And then I can divide that by 2 to find my halfway back down to the ground height. And then I can go back and use this equation again to figure out how fast I'm going at that particular height right there. So I could go back in and say v squared equals v0 squared plus 2a delta y with my new halfway height right here. Still have the same acceleration, still have the same initial velocity, and now I'm solving for what is v when it's halfway down to the ground. Once I figure that out, I can plug it back into here and figure out what the angular momentum is. So yeah, it's a bunch of steps, but it's doable, and you can look at my solutions, and I have it inside in my solutions. Okay, what is the torque on the ball at about p due to the gravitational force when the ball is at its maximum height and when it's halfway back down to the ground? Okay, so this time I don't really have to worry about the velocity, so I'm just looking for torques. And the torque formula, here it is over here, it's R cross F. So I get R cross F, and that's going to turn into RF times the sine of the angle between them. Once again, I could also mimic this as R perpendicular times F, and that kind of takes care of the sine theta. So I'm going to use this R perpendicular distance right here. And now I just need to figure out what the force is. So if I draw a free body diagram, there's the ball. No matter where it is, halfway up, halfway down, wherever it is, it's just going to be mg right there. So that's what the force is going to be, is just mg, and then that's it. And the torque's going to be the same because the R perpendicular is the same, and the force does not depend on the height of the ball. So halfway down to the ground, or when it's at its maximum height, it's still going to have the same torque right here. It's just going to be R perpendicular times mg, and the R perpendicular is this distance right there. Okay, I'm going to stop here, and then I'm going to make the next video about the next problems.